Hello everyone, how you doing? This is a video for week 4 for my Algebra 2 class, Solving Linear Systems and Inequalities. For week 4, read the sections in our CK12 textbook. Use it as a good resource this week. Make sure you watch this video, use it as well while you're working on paper pencil assignments or any other assignments for this week. The objectives for week 4, here's what we'll be learning. We're going to be talking about if I give you a linear system of equations, we'll look at how to solve it using the addition method. So a whole new way to solve linear systems. If I give you a linear system of equations, can we rearrange both equations into standard form to use the addition method? We're going to recognize linear systems with infinite and no solutions, just like we did last week. We're going to be able to explain why the addition method of solving a linear system of equation actually works. Finally, we'll switch gears. We'll represent and solve problems with linear systems using the addition method, and then we'll get into some inequalities. So I give you a problem. Can you represent it with a linear system of inequalities, and then find solutions to linear system of equalities using graphs? Okay, we got a lot going on here with systems this week. This is our last week on systems. So let's get started. So if you remember, a linear system of equations is used when we have multiple constraints in a problem. We need two or more equations to represent what is going on. We can represent a linear system with a graph, two equations, or a table of values. And each of these three are different representations of the same relationship between variables. If you remember, when we talk about a solution to the linear system, a solution is the intersection point, if I'm graphing the two lines. It is the x and y values that make both equations true. And on a table of values, it's the x value that's the same y value for both equations. And so we talked about graphically on a table, and algebraically we have lots of ways where we can find and recognize the solutions. So what we're going to start with is pick right up and learn another algebraic way. We learned the substitution method last week. It works pretty well. You just have to get one of the variables by itself and substitute it in. But it's not always the easiest, and there's another method that we can learn called the addition method. So here's the steps in the addition method. You want to get both equations into standard form. Multiply one or both equations to get terms that add to 0. That's kind of the key. We'll talk more about that. Add the two equations together, solve the equation for the first variable, back substitute and solve for the other variable, and then check your work using a graph. We'll go over a few examples of the addition method. If you look at your paper pencil problems as well for this week, there'll be several more examples that you can use to refer to as you're getting this method. But we're going to use these steps 1 through 6, and we're going to solve this system right here. 2x minus 3y equals 9 and 5x plus 3y equals 30. We're going to go through each of these steps slowly. This is an easier example, and then we'll get progressively harder in the next couple. All right, first step. If I want to use this method, I need to make sure both equations are in standard form. If you remember, standard form is that whole ax plus by equals c, where my x and y terms are on the same side. A, b, and c are all integers. A has to be a positive whole number, so there's no fractions or decimals. That's the first thing we want to do, is rearrange them in standard form. The addition method is the best to use if they already are in standard form. So here I've got 2x minus 3y equals 9 and 5x plus 3y equals 30. These are already both in standard form. They're already lined up with my x terms, they're already lined up with my y terms, and they're already lined up with my constants. So step 1 is done. All right, now step 2 may or may not need to happen. We'll go over some examples, but I need to make sure one or both equations, when I add them together, I have two terms that add to 0. So what we mean by that is we're using the addition method, right? We know in algebra, if I have an equation, I'm going to do a quick example here. If we have x equals 2, I can add 5 to both sides. As long as I add the same thing to both sides, I can get a new equation, x plus 5 equals 7. This is the same as this, and all I did was get there was add the same thing to both sides. That's why the addition method works. 5x plus 3y is the same thing as 30. And so when we add 5x plus 3y on the left side, and I add 30 to the right side, it's keeping the same equation. I'm adding the same thing to both sides, and so the resulting equation should be equivalent to the first equation. Now watch what happens when we add these together. 2x plus 5x, I can only add like terms, right? 2x plus 5x equals 7x. Negative 3y plus 3y, those are opposites, they turn into 0. 9 plus 30 equals 39. If I delete out the 0, we just really have 7x equals 39, and I can solve for x by dividing both sides by 7. X equals 39 divided by 7. 7 goes into 5 times with the remainder of 4. There we go. That is the first part. We actually did step 2. We did not need to multiply because when I added them up, I had two terms that did add up to 0. Negative 3y plus 3y, those added up to 0. That took care of step 2, and then we went ahead and did step 3, adding the two equations together. And then we did step 4, we solved the equation for the first variable. We see this intersection point in the solution happens when x is 5 and 4/7. Now we still have to do steps 5 and 6 because we still need to know the y value, right? I found x, but what is y? Well, in this case, I can either back substitute. I know x is 5 and 4/7. I can put that in now for x and solve for y. And that's what I'm going to do here. I'm going to take the first equation, 2x minus 3y equals 9, and put 5 and 4/7 in for x. So we got 2 times 5 and 4/7 minus 3y equals 9. And now we're going to solve this out for y. I'm going to change 5 and 4/7 back into 39/7 to make it a little easier to multiply by 2. And now 2 over 1 times 39 over 7 is going to give me 78 over 7 minus 3y equals 9. Okay, we got some fraction stuff here. I'm going to subtract 78/7 from both sides. And we got negative 3y equals 9 over 1 minus 78 over 7. I'm going to change that in the right so I can subtract. So I got negative 3y equals, I'm going to multiply by 7, so that turns into 63/7 minus 78/7. 63 minus 78 is going to be a negative 15/7. So negative 3y. And I'm going to multiply both sides by negative 1/3 to get rid of the negative 3. Multiply by negative 1/3. And y is equal to positive 15 over 21. Whew, that was a lot of work, right? The fractions kind of made that one pretty ugly. But there we go. We have the intersection point happens when x is 5 and 4/7 and y is 15/21. So about, roughly about 5.5 and then 3/4. So there we go. We just back substituted and we solved for the other variable. We know x and y. This is my intersection point. But now ultimately, especially when we have a lot of algebra and a lot of fraction stuff, there's a lot of opportunities to make mistakes, right? So let's check our work using a graph. We're going to graph this system and just make sure my intersection point looks right according to my calculator here. So let's go ahead and take a look at the graph. All right, here I am at the graph. So there's my system of equations. I graph both lines. And if I look at where they intersect at 5.571, which is about 5 and 4/7, so I'm feeling good about that. And 0.714, that is about the same as 15/21. So I'm feeling really good about my results. My graph is verifying my work that I did algebraically. Okay, let's take a look at another example here. Sometimes when I'm using the addition method, again, adding the same thing to both sides, sometimes I need to multiply one of the equations to get terms that add up to 0. For example, if I add these right now, I get 4x plus 1x to get 5x. And I have y minus 3y, which is going to give me negative 2y equals 26. Well, the whole point of adding them together in the addition method only works if I can get two of these terms to add up to 0. So if I look at my x terms and I look at y terms, neither in this case added to 0. So I can't get anywhere. I can't solve for x. I can't solve for y. So I need to scratch this out, and I need to think about how can I rearrange this system of equations so that when I add my x terms or add my y terms, I do get 0 and one of the variables canceling out. Well, what I'm going to do is I have a minus 3y on the bottom here. It'd be nice if I had a plus 3y on the top. So to get that, right now it's 1y. I'm going to multiply everything in the top equation on both sides by 3. So I'm going to do 3 times 4x, 3 times 1y, and 3 times 0. So now we've got 12x plus 3y equals 0. 3 times 0 is still 0. And on the bottom, I still have 1x minus 3y. I have the same equation that I had before, equals 26. Make sure, again, if you're multiplying an equation, multiply everything on both sides of the equation. A lot of times students will say, well, I need to multiply the y by 3 to get 3y, but they'll forget to multiply the 4 or the 0. Make sure everything on both sides is multiplied. But now look what happens. We changed one equation, we multiplied. Now if I add them together, 12x plus x gives me 13x. 3y minus 3y, there's my 0, so I don't even need to write it, but it equals 26. This is easy to solve now. Divide both sides by 13 and x equals 2. I like that. If x equals 2, let's substitute it in. So 2 minus 3 times y equals 26. Subtract 2 from both sides. So negative 3y equals 24. Divide both sides by negative 3. And my y value equals negative 8. There we go. We solved the intersection point. The solution to the system is when x equals 2, y equals negative 8. I could graph this now and verify my solution as well. But there you go. That was an example of when I needed to actually multiply. I needed to change the original system by multiplying one equation into a way so that I could then get 3y minus 3y to get 0. All right, ramping up the difficulty, sometimes you also have to multiply both equations. So here we go. We've got 2x minus 5y equals 15, 3x plus 7y equals 8. Right now, my x's don't add up to 0, or my y's don't have to add up to 0. So I got some work to do, right? I got to rewrite this thing. I got to do some multiplication. Well, if I look on this one, I'm going to work with subtracting the x's here. I want to get these to be the same coefficient, just one positive and one negative. I'm going to multiply the top by 3. So I'm going to have 3 times 2x, 3 times negative 5y, and 3 times 15. And I'm going to multiply the bottom by negative 2. Negative 2 times 3x, negative 2 times 7y, and negative 2 times 8. Let me rewrite the system now, and we'll see how it makes it work out. So 3 times 2x is going to be 6x, minus 3 times 5y is going to be 15y, equals 3 times 15 is 45. That's the first equation. We just multiplied everything on both sides by 3. Now let's take the bottom equation, multiply everything by -2. So -2 times 3x is going to be -6x. -2 times 7 is going to be -14y. Equals -2 times 18 is -16. There we go. Watch what happens now when I add these together. Because we multiplied intentionally, I got 6x minus 6x gives me 0 x's. I'm glad. So -15y plus -14y is going to be -29y. And 45 plus -16 is also going to be +29. Well, look at that. If I divide both sides by -29, I get y is equal to -1. That's a nice, clean answer. Obviously, you don't always get nice, clean answers. Our very first example was an ugly fraction. There you go. There you go. This one worked out pretty nice. I've got my y value. I still need to find x. But let me show you another cool trick here. Rather than back substituting, what if I multiply again? What if I this time want to get rid of the y's and solve for x? Well, this time let's multiply the top by 7 and the bottom by -5. So we'll use our multiplication techniques again. On the top, if I multiply by 7, I get 7 times 2x is 14x. Minus 7 times 5 is 35y. Equals 7 times 15 is 105. So that's the first equation. I just this time multiplied everything by 7. And on the bottom, let's multiply everything by -5. -5 times 3 is going to be -15x. -5 times 7 is going to be, oops, I almost just made a mistake there. Look at that. I put 7 and -5, but I already have a negative number on top, so I need to keep the bottom positive to add to 0. So I'm going to multiply by +5. I've caught that mistake. So really, this becomes +15 plus 35y. Hopefully that didn't throw you guys off. And +5 times 8 is going to give me 40. All right, now let's add these two together. 14x plus 15y is going to give me 29x. That's kind of interesting. My y's turned to 0 because I got -35 plus 35. I like that. And then 105 plus 40 is going to give me 145. So divide both sides by 29. And x is equal to, well, let me get my calculator. I believe this is 5. 145 divided by 29 equals 5, yes. So there, we didn't even have to back substitute. We just multiplied both equations. We multiplied one way so that our x values turned to 0 and solved for y. And then I went all the way back and I multiplied a different way to make sure my y values turned to 0 and I solved for x. But there we go, we got the solution. When x is 5, y is -1 for both equations, and that's my solution. I should be able to see that on my graph to verify as well. There you go. That is 3 solid examples of the addition method, how it works. Again, the whole idea is it works because we can take an equation that's equal. We can add the same thing to both sides to keep the same equation. Annalise, you cannot sit outside the door and do a squeaky voice, okay? All right, honey, it's too loud. All right, let's do a word problem. Everybody loves word problems, right? Using the addition method to solve a problem. We have 1 pound of a mix consisting of 30% cashews and 70% pistachios. It sells for $6.25. A 1 pound mix consisting this time of 80% cashews and 20% pistachios sells for more, for $7.50. Okay, knowing those items, how would a mix, if it's a 50-50 mix, 50 of each type, how much should that mix sell for? All right, we got some work to do, and you might be even saying like, what? That's so confusing. Well, let's put it together. We know we have 1 pound of mix, so 30% of 1 pound would be 0.3 pounds of cashews and 0.7 pounds of pistachios, right? Now, if it's 0.3 pounds, the unknown is the price per pound of cashews, right? I don't know how much that is. And P, I don't know the price per pound of pistachios. I know how many pounds I have. I don't know the price per pound. That's what I'm going to solve for. Okay, so if I have 0.3 pounds at C, that cost per pound of pistachios, and I add to that 0.7 pounds of P, the price per pound of pistachios, I know that in total, the amount I paid for cashews and the amount I paid for pistachios was $6.25. That is one equation that fits that first scenario. Again, remember we look for totals and things that add up to the totals in a lot of these problems. The next case is I have more cashews. This time I have 0.8 pounds of cashews, but only 0.2 pounds of pistachios, 20% of 1 pound, remember, that's kind of key, the 1 pound. But this time it's more expensive, it's $7.50. But look at what we got. We now have a system of equations, two scenarios that model the same problem. And we can use the addition method to solve out, well, how much is it per pound for cashews and how much is it per pound for pistachios? Okay, I'm going to use, let's see, if I want to get rid of one of these variables to go to 0, I'm going to multiply the top by -2 and the bottom by 7. I'm going to cancel out the p's here and then solve for c first. So my new equation becomes -0.6c plus -1.4p equals -12.5. On the bottom, I've got 5.6c plus 1.4p equals 49.50, 52.50. All right, this is a nice system because when I add them together, my p's go to 0. I like that. So -0.6c plus 5.6c is going to give me just 5c. That goes to 0, and it's equal to, oh, these add together nice too. Look, those add up to 40. So 5 times c equals 40. Divide both sides by 5, and c equals 8. Well, what does that mean? Well, it means the price per pound of cashews is $8 per pound. That seemed to make sense, right? In the context of the problem. If I got $140 per pound, then I would think, oh, I did some math wrong somewhere. So $8 per pound, it makes sense. All right, I still need to find out, well, how much does it cost for pistachios? So let's go back now and solve for pistachios. So, and if I know C is 8, I'm going to put 8 in for C. So 0.3 times 8 plus 0.7 times P equals 6.25. And I'm going to solve for P. 0.3 times 8 is 2.4 plus 0.7 P equals 6.25. Subtract 2.4, let's just solve for P. And we got 0.7 P is equal to, I'll do some math here, 6.25 minus 2.4 is 3.85. And now let's divide both sides by 0.7. All right, I get P equals 5.5. So what can we take from that? Well, P is the price per pound, so it is $5.50 per pound for pistachios. Now you may think we're done, right? Whew, we solved for C, we solved for P, we're good. But we actually have not solved the problem yet. Remember, go back to that problem. What are we supposed to find? How much would a mix of 50-50 of each type of nut sell for? All right, so I got to go all the way back and use P and C that I found and say, okay, $8 per pound for half a pound of cashews plus $5.50 per pound for half a pound of pistachios. What is that going to add up to equal? Well, that's $4 for the cashews, and that's going to be $2.75 for the pistachios. So it looks like I'm going to end up paying $6.75. Which it makes sense, right? It's right in between the $6.25 for mostly cashews, or sorry, for mostly pistachios, and the $7.50 for mostly pistachios. Hopefully that's a good example of using a word problem, translating into a linear system, and then solving it out using the addition method. Okay, the last little thing I want to go over is sometimes we have situations where we need to model a system of linear inequalities. So I wanted to talk a little bit about inequalities. We're going to do some graphing with them, recognizing solution sets to inequalities, and then we'll be done. So here we go. We've got a system of inequalities, 3 of them. Y is greater than 2, 3x plus 8y is less than 45, and y minus 10 is greater than 4x. And these are all 3 constraints. I want to know, well, what are all the points, what are all the x and y values that make all 3 of these true? Sorry about that. The best way to do that is to go straight to the graph, and then we can use the graph to help us think through situations. So I'm going to graph all these in the Desmos calculator here. Let's go take a look at that. Okay, here I am on the Desmos calculator. Let me get just that. Okay, so y is greater than 2. There's all 3 inequalities. Now watch what happens when I turn them on. So there's the first one. There's all the points where y values are greater than 2. Notice there's the point on the y-axis of 2. So this point right here is when x is negative 4, y is 4. That's a solution. That's a solution. All these points are solutions. There's an infinite number of solutions. We remember that when we did linear inequalities in Algebra 1. But I've got a whole system. So now let's look at, well, what are all the points where this inequality happens? So if I turn this one on, we can see that it's blue, the other's red, but there's this overlapping part where it kind of forms a triangle, right? This triangle, this sort of purple area, represents all the points that work for the first inequality and the second inequality. So you have to think of it as like puzzle pieces or pieces that are looking for where they overlap, and that's the system. But I have 3 inequalities to deal with, so let's turn on the third one now. So the third one is green. And the system for the solution to the system for all 3 inequalities is where all 3 overlap. So there's my green part, my red part, my blue part, all interlap at this sort of polygon area right here, right? So the corners are at -2 and 2, and -1 and 6, and then there's boundaries formed by the other inequalities. So if I want to find a solution, it's got to be within this area. So one solution would be when x is -8 and y is 4. If I plot that point, that's in the solution set of all 3 inequalities. Another solution would be -10 and 8. There we go. That's also in the solution. A point that would not be in the solution would be -4, 8. it's a point, it's in the green area and the red area, but it's not in the blue area. It's not overlapping all three. So that is not a solution. In fact, even the corner points are technically not solutions as well, because anything on the line is not a solution. So go. These 2 points are solutions, and that's how you find solution sets to systems of linear inequalities. You're looking for points that lie in where all the graphs overlap. All right, so let's recap what we did. We did a linear system of equations. We learned all about the addition method. We did a lot of examples about rearranging both equations, the importance of standard form to be able to add them up together, add the x's and the y's and the constants all lined up. Linear systems with infinite no solutions. Again, as you're solving them, be aware of if you get a false statement, if the variables cancel out. You want to be able to explain why the addition method works. We're just adding the same thing to both sides, which is a thing I can do in algebra. As long as they're equivalent, I can add the same thing to both sides. We represented and solved a problem using linear systems, and then we did a little bit about how to represent linear systems of inequalities with a graph and how to find solutions to linear systems of inequalities. Hopefully this helps you dig in to the week 4 problems, and let me know if you have any questions.